Hi viewers, uh, my name is Malasa. In the previous tutorial I have shown you the design of the steel structures. In this tutorial I will try to show you the remaining parts of the design of the steel warehouse and the connections design as well as the foundation design. In the previous tutorial of part 2, I have shown you the detailed design of the main column, the corner column, the end column, the rafters. That means the main rafter and the edge rafter, the row purlin, the tie beam, and the the critical polling design. So now we will continue this tutorial. Here, this is the model that I have designed in the previous tutorial. Now here, just what I'm going to show you. I have made some modifications on the cross sections of the critical member of the roof purlin, and as well as the member definitions of some structural member of the warehouse. Here, I have already analyzed this member, and now here there is one error here. This error is the no convergence of nonlinear problem, case number 30. Robot converges the applied load just to bring the structures in equilibrium. So some load cases may not be converging to give or just to satisfy the requirements of the equilibrium. So in that case, we need to just make some adjustments of the setting in the analysis types dialog box. So here the load that cannot convert is case number 30. So just we need to make some adjustment or some revision on the setting of the analysis tab. Just click the analysis tab and just go to the case number 30 here, just case number 30. So here case number 30, where is it? This one. This load cannot convert it to satisfy the requirements of the equilibrium conditions. So in this case, just we need to go to the case list here and select the case number 30. Case number 30 here. Case number 30. Yes, add. So, and then set a parameter here. Set the nonlinear analysis parameter here. So robot has by default a load increment number of 5, so we need to increment this into 10, and the maximum iteration number of one increment, it is 40, so I can make it 100. So click OK. Now click OK. So here the performed operation will call the changes in the database. So robot needs the recalculation of all the structural members. So do you want to continue? Yes, I want to continue because the analysis type is changed. So click yes. So here just run the calculation based on this modification. Run the calculation. Now robots analyzing all this structure based on the modified analysis tab, and then yes, click yes. So here, as it is taking more time or so, okay, here the analysis is completed. Now there is no error. There is one warning, no problem. Warning. Maybe corrected, or maybe let it be as it is. So here, the design verification will be checked once whether the provided cross sections are adequate or not. So now before that, now let me brief you the member definitions that are modified in this tutorial, which is the part 3. The previous tutorial of part 2, we have defined the members, but some members are modified because just to be economical, we need to categorize the critical sections and the critical member with the specified cross section here. As you see, let me see the top view here. This is the top view of the warehouse. All these are the purlins which run from here to this, which is perpendicular to the rafter. And now the stress, there is the 4 critical purlins that need more cross sections are located here, like this. Here 1 purlin, 2 purlins, 3 purlins, and the 4th purlin. So those purlins must be grouped in one group, because if we group those purlin with all the rest purlins, so the sections that we provide for all those cross sections must be also provided to the rest of the purlin. So here we will use high cross section as those critical member. So we should not use this higher cross section for the rest of the purlin. So in order to be economical, we need to categorize the rest of the purlin, non-critical purlins as one group and the critical purlin as one group. So accordingly, the member definition should be done as per the provided member definitions. So here there is this here this is the warehouse. So this warehouse must be designed in such a way that the equilibrium requirements has to be satisfied. So here we need to go to the yeah. So just go to the member definition here. There is the word purlin here. The member definition for all the purlin is defined with this word purlin here, just like this. This is the member definitions assigned to all the purlin. The purlins are pinned here in order to minimize the high consumptions of still. So just to view which members are pin indeed or not, just go to here and right click the pin indeed here. All the wall purlin as well as the row purlins are pin indeed here. Those marks show the members are pin indeed. So here, just come to here. All the purlins, as all the purlins are restrained with the roof cover in the direction of Z. So the Z-axis must be, the buckling length coefficient in Z-axis must be 0, because we will not consider the buckling length coefficient in Z direction. So no need of just here, just like the, you need to select this one. But here there is a roof cover here and there is a roof cover here. So the Z direction for the wall purlin is in this direction. So in Z direction, the wall purlins are restrained. So there is no buckling in Z direction, and similarly for the roof purlins. So now here, but in the case of a y direction, or in the case of the weak axis here, this is the weak axis, which is the major axis. Now in this direction, the purlins are not restrained, so that is why we need to provide the buckling length coefficient is 1 in these directions. So here, it is pin indeed. This indicated that the member is pin indeed, both at the top and at the bottom. So in this case, we need to use the buckling length coefficient, which is 1. So here, just like this, we need to make save, which is already assigned. Yes, we can click yes. So close this one. So this is for the member definitions of both the wall purlins as well as the roof purlins. And when we come to also here the tie beam, here this is here there is a tie beam. This is a tie beam. When we come to the tie beam also here, the tie beam is not here. When we come to here, the tie beam is also, it is pin indeed, as you see here. So here the tie beam, Z is in this direction and Y is in this direction. So in Z direction, there is a buckling in both directions. So as the member is pin indeed, so the buckling length coefficient both in Y and in Z direction is 1. So here 1, 1, and also here this is selected here, and also this is selected here. So here now and when we come to also the additional sets of the member parameter, the co-deforming member, such as the RHS, SHS, CHS and Z section, and the C sections are 10-volt members. So we need to make thick 10-volt section, so that robot will consider all the sections are 10-volt section for the buckling analysis. Okay, now save this one, and yes, and now close this one. Okay, the other is the main rafter definitions here. So close this one, and in order to make the endpoint markers here, and then just in order to view which member type of definition is assigned to the edge purlin, and which member type definition is assigned to the internal rafter. So we need to just select this one. Sorry. Okay, just right click here and then just object property, so we can see which member type definition is assigned here. So here edge rafter and so now, okay, sorry. Okay, sorry. Just come to here. The main rafter definition is assigned to this. Okay, here. Just come to here. The main rafter definition. This is for the internal rafter. So here, as the internal rafters, there is buckling in both direction, both in z direction as well as in y direction. That means in major axis as well as in the minor axis. So the buckling length coefficients of the internal rafter will be here. Here this is a fixed support, and here this is a fixed support, and this acts as one beam. That is one rafter, one member. So the buckling length coefficient has to be taken as 0.5, just like this. Yeah, this is 0.5, which is int fixed at both points, just like this. Okay, sorry. Here, this is a fixed, and when we count also in z direction, it is in z direction, there is restraints at some points of the rafter. Here there are 1, 2, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There are 10 purlins at the upper flanges of the internal rafters. So we need to use these options here. There is restraints on the intermediate points of the internal rafter. Just this one. And when we come to also here, there is also here this is already previously it is defined, so no need of redefining it. So here this is not a team member. The rafters are, well, the I sections, and I sections are not the team node section. So we should have to avoid selecting these options. Okay, and when we come to also here the service, the limits of displacements and deflections are stated here. So we need to select the final deflection limit here, just that in y direction and in z direction, that is L over 200. L is the span or the length of the rafter. And for the purlins, the length of the purlins from one end to the others. Like for the column also, from the the length of the total height of the columns. Okay, here you just no need of selecting the live load and the the node displacement global system here, because robot will automatically calculate those values. Okay, here just we can click save. And now also here when we come to the sorry, just sorry, no, sorry, no. Okay, here Okay, sorry, just right click here, the object property. Here there is a main rafter definition. Also here it is assigned to this one, but here in the main rafter definition, this one is here. Sorry, we need to apply the main rafter definition at the edges here, because at edges, so here this is fixed int, so we need to put the buckling length coefficient 1 in y direction and the buckling length coefficient in z direction, as also sets as auto, because robot will automatically calculate the buckling length of the member. Okay, so here just we need to here this is 254, so we need to 254 here, just put 254. So here the okay, here when we come to here, so select at point with the adjoining element in the buckling apply here, because in y direction there are columns here, so we need to sorry sorry here at point here, we can copy this because it is similar to the internal rafter, except supports at the intermediate pointers of the vertices. Here it is. Sorry, just it is 254. So here come to here. And here 254. So we need to delete this one. So here we need to use this one, just like this, and here the rest are similar, 254. And in the direction here there is a support at the adjoining positions of the rafter here, so we need to click OK. So save this one. Okay, here we need to close this one, and we need to assign this property to the edge rafters. So we need to select these similar cross sections here. So apply this. Okay, perfect. When we click here, object property, so we can see the member definitions here. Okay. Okay, now let me check once again the edge rafter here, and object property, and then come to DCT, the main rafter edges. The main rafter edges, meaning here this member definition is assigned, this one. Good. Okay, now second here, so the rest one is we have checked the member type definition of the purlin, and the rafter called the edge rafter and the internal rafter, and what's left is the column. So here, now go to the member definition once again, and then here the column, the main column, or is it the main column? Here the main rafter, okay, just go to the column here, in object property, here there is simple bar 251. So we need to apply the member to the columns. Okay, when we come to also the member type definition of column, let's once again check it. When we come to here, the columns are fixed and support, so we need to make the buckling length coefficient in y direction is 0.5. Here y direction is this one, and in z direction it is an automatic determination because there are braces at the upper flanges of the column. Here in z direction, in this direction, there is an intermediate restraints, so we need to make an automatic determination of the buckling length coefficient. Okay, this is for all the columns. So what is left is the braces here. We need to check the braces here also. So we need to go to this one here. There is no buckling in y and in z direction for the braces, because braces are attentions only members that cannot carry load coming from the wall, and as a result there will be only attention force. The moment and the shear will be 0, so no buckling at all. So we need to assign this to all the braces here. Select by cross section. Now apply. Okay, here member type definition is applied. So here simple bar, list over here. So member type definition is not applied to the brace because braces are not load carrying member. And when we come to also the other, the tabbing, here the tabbing, this one, it is the buckling length coefficient is 1. Sorry, the buckling length coefficient is 1 in y direction and 1 also in z direction. Okay, here teamwork section. So all the member type definition is defined properly, and also here this is the critical purlin here. It is the rectangular hollow section having similar depth with the Z section here. So now right click here and object property. So here it is a wall purlins pin is applied. This is the member definition for this one. The member definitions for all the purlins are the same. Okay, now let me run once the in the code design. Run the code. Okay, it needs reanalysis. Okay, run this one. Okay, it's good. It passes the requirements with a section of 200 by 10. So now select all the cross sections once again. Okay, this one. Now calculate with an optimization. Ultimate limit states load. Then okay, we will run the analysis again after checking the code group design. Here the corner column. The corner column will have a section of here 300, which is an optimized cross section. In our robot optimizes the cross section that has to be used for the corner column, the internal column, the main column, the rafter, the purlin, the tabbing, the critical purlins. For all those members, robots selects the optimized cross sections for the design. Now here this is the we have to use the cross sections having higher weight of the higher we need to use a higher weight of cross sections than this blue color. So this is the minimum cross section that is recommended by robot for the specified elements. If we use a cross section less than here 284 corner column, so the column will fail. So that is why robot recommend this the minimum size of the cross section here. This is in blue color. So we need to select the cross section which is relevant for the workmanship as well as for aesthetics. Now here robots finished designing all the members. Here so now there is some problems on zero purlin. Here this the utilization ratio of 2.6 for arrow purlins of here. And so here so we need to see which member is failed. So it is member 60 properly. Here member 60. So here now let me see it's not happening. Okay, this member, good. This member. So we need to match So here we need to run the design once for the critical purlin here. Run the code. So robot selects the preferred cross section for the critical purlin design. Here, this one is selected here. Having it is 5 mm thickness. So we need to change for all. Change all. So all those cross sections are changed. Okay, no. Don't not change it still now. Change. Perfect. Okay, all members are changed. So now let's run the calculation. Here, okay. Good. So now let me also check. Now, so here. Now let me select all the member and check whether all the members passes the requirement or not. For both ultimate limit state and serviceability limit state. Now, okay. Here now, robot is checking the member verifications. This is for the internal rafter, and this is for the column. And here this member is failing. I'll click this one. The member 65. We're gonna check member 65. Oh, for typing. Just for typing. Typing 65. robot can select the section because the design process is being undergone. After the completion of this member verification, now I can show you the which member is failing here. This one. All the sections are passing the design verifications of the member, except this one. Here all the member passes. So here robot structural analysis professional recommends the optimum cross section to every members. Here all the members pass the design requirement for both serviceability and ultimate limit state. Because here I have already selected the ultimate limit state and the serviceability limit state requirements. Robot structural analysis professional is completing all the designs of the structural members. Around 10 groups of structural members are being designed with an optimum cross sections. Here it's completed without any error. Now when we come to the result here, all the members are passed the design here except the typing. I'll show you which member is failing here. Okay, good. Now T65, typing 65 and typing 65 and typing 65 and here go down. It is 277. 65 here. Okay, so I think it is difficult to select here. Just now let me select the typing here, the cross section, and opening a new window. So now show the member, the part number here. Okay, now here there is not that member here. Okay, here now let me find this member 65 here. So now search for here. This is the member. Perfect. This is one of the member that fails the design, and the other is 277. 277 here. Okay, this one. So here I have to redesign it once again. Okay, just to go to the code group here and select it and type in here. So run the calculation for ultimate limit states. Run the calculation. Now robot will select the optimum cross section. Here it is, the cross section is 7.1, 140 by 80 by 7.1 is selected. Okay, now here change the cross section for all the members. Okay, now the color is not that much visible here, 148 is 7.1. Now let me change the color. It is 140 by 8, this one. So click this one, double click, and then change the color. Okay, which is, I think we can make it just like this. Okay, this one. Okay, this one. Okay, add. Yes. Then the color is changed here. And now let me check the group code verification. Which is 9. Run the calculation. Okay, sorry. This is for the ultimate limit states, which is okay. And for serviceability limit states, okay, it's okay. Now let me check once and so check for all the member for both ultimate limit states and the serviceability limit state for this verification. Now robot check the final code group verification of all the members. Here the type beam will pass the requirements. Very good. Here the top beam with this cross section passes the design for both the ultimate limit state and the serviceability limit states. So our code group verification is okay. So close this one. Then just check the code group design for all the members. This one. Run the calculation. Be sure that the ultimate limit state is selected here. Sorry, cancel this one. So select the ultimate limit states for the group code design. Enter. Here now, robot structural professional analysis completes all the designs of the structural members of a steel warehouse. As you see here, all the member passes the design requirement for both serviceability and ultimate limit state requirements. Here, all the member passes. So we can use here 300 for corner column And we can use also here 300 cross section of steel for internal column, and we can use here 400 for the main column, and for edge rafter we can use have 300, and for the main rafter we can use have 400, and for the roof purlin we can use 200 by 24 z cross section, and for ware purlin we can use 150 by 15 z purlin, and for brace we can use a solid bar, round bar of it is 28 millimeter in diameter. You can see here this cross section is you can it is around it is 38. So we can use the 38 cross section for brace material, I mean for brace element. Here there is no 38 cross section here, but we can use it because this member, and once we can check it. So here we can select all the members, and we can copy this one. Okay, now let me check first the member verification for both ultimate and limited. So it is 38. So we can change these cross sections. Okay, anyway, we can change these cross sections by 30. Here, change all. So good, we can run the calculation. Those changed cross sections of brace. So now robots checks the design of the brace based on the changed cross sections of the elements. Now all the elements passes with a round bar of 30 millimeter in diameter. Okay, good. So we can use a 30 millimeter round bar for brace elements, and we can use also the rectangular harrow section with 200 by 10, and the cross section, you can see here the cross sections, that is 200 by 10 by 4 as the top tab. Okay, here. Okay, so here for row purlin critical, that means for those elements, for this and for this and for this and for this, that is the critical row purlin. Here there is high internal force at this zone, because it is the intersections of the brace. That is why we have to use higher RHS instead of the purlin. Okay, row purlin critical, we can use 200 here. We can click here 200 by 10 by 200 by 100 by 4 millimeters. So we can use this one. It's okay. So when if you see the utilization ratio, it is 0.91, which is economical cross sections. No, I mean this one, it is 0.21. So this is for the design of all the members. Okay, good. Now close this one. Now let us design the footing. So here, in order to design the footing, here we have to make visibility support here. Okay. So we need to design the footing under, the in the column here. So we need to. So here, select. Here we have to select. Okay. Here the supporters are selected, so we can be sure that here there's no this have to come to here when we select the support. Okay, so click, go to the here we're at the design. So here now we have to get the model. And then just click this provide reinforcement of RC element here. So all the logics will be exported to the foundations. So we need to check whether all the logics are transferred to the foundation or not. Here the load transferring dialog box will be coming here. So we need to click this and then click OK. So now robot will assign a footing to the selected supports of the warehouse. Now here there is the menu here, structure, the foundation view, the foundation level, the foundation reinforcement, and the foundation node is coming here. So here click the the tools here, the customize, and open the layout from the templates. Now the template is coming. So here just click this one. Now here this is the previous foundations. So we need to delete this one. Okay, when we come to the structure, here the footings are assigned, but here the similar size of footing is applied to all the foundations. Even we can group for the the footing under the main column and the footing under the end column. But for simplicity of the design, we can select for both. So here, which one is the okay? Just come to the foundation view here. Delete this one. Okay. Okay. Good. Perfect. Here, we have already selected this one, and we need to design this one. And we will also design this part here. This is I could just renaming it. Okay, foundation 342. So create another. Create here the foundation. Okay. This is also foundation under in the column. So we need to design first this one. Okay, here, by default, the length and the width of the footing it is 2 meters, and H1 is this one. Let me use H1, it is 0.5, and H2 it is 1 meter. That is the height of the foundation, and fix the height of the foundation and the depth of the foundations. And then here this is the size of the column, that is 0.6 by 0.6. Now no centricity at all. Fix it, and then go to this one and bolt it. Here this is the plate size, that is 0.5 by 0.5. So the optimization will be square footing, then apply. Robot will apply this foundation size to the foundations. Okay, so we need to run the calculation. Start the calculation of the foundations, but the ultimate bearing capacity of the soil is taken by default from the robot structural analysis foundation investigations parameters. Now let me define first the ultimate bearing capacity of the soil here. Just come to here. This is the soil property. You can use the software to determine the ultimate bearing capacity, or you can use the geotechnical reports coming from the laboratory. Here, okay. Now, the type of soil, maybe it is clay, or you can change as you like based on the geotechnical report. And the type of the soil is clay and silt, or you can change based on the geotechnical report. And the level where this soil is obtained, just you can put the depths and the thickness and the color, the weight, the unit weight. It is you need to the unit weight in kilogram per meter cube, and the unit weight of the solid in kilogram per meter cube. Here the friction angle, the this Here there is also the friction coefficient, it is 0.47. So the friction angle, now let me take this 30 degree, and the friction coefficient is, so friction coefficient, it is 0.47, and the equations in megapascal is 0.06. So you can use all these parameters. You can use all those parameters, and then just click apply. Okay. But before that, here this the unit is in kilogram per meter cube. The question is, it is in megapascal. It's also good in meter. Okay, now come on this one. So now robot will calculate the size of the foundation, the optimum size of the foundations. Run the calculation. Here the size of the foundation will be optimized. Good. It is 2.5 by 2.5 meter size of the foundation is adequate for the ultimate bearing capacity of the soil, which has been defined before. Okay, now this is good. Now run the calculation for this size. Very good. Let's come to the foundation result. Okay, this shows the capacity ratio, which is greater than what is okay, the contact surface ratio, which is greater than this value. So all the parameters, the value of all the parameter exceeds the limiting value. So this shows that our foundation size is okay. Okay, when we come to the combination coefficient, this is also okay. The ultimate limit state, this is for serviceability, and this is for the ultimate limit state. Okay, it's very good, a very good result here. All those are the combinations, I mean the design combinations that are considered desirable while designing the foundations. Okay, very good. Now here let's come to also the foundation reinforcement here. All this is the default value here. Just click this one, typical reinforcement. Now this is the typical reinforcement. So I wanted to first delete this default reinforcement here. Now delete all. Sorry, delete. So now click the typical reinforcement button here. Now this is the geometry, the bottom reinforcement. Here this is the bottom reinforcement in X and in Y directions. So now let me select it is 40 millimeter in diameter for both X and Y direction at the bottom zone. This is the grade of the reinforcement, and the hook, it is 90 degree. And the spacing of the reinforcement, now let me use it is 14 centimeter, and later I will increase or decrease the spacing of the reinforcement based on the calculated moment. And when we come to it, it's hook 90 degree, and now let me use it is 40 centimeter spacing. So this is the size of the cover C1. This is the size of the edge cover, and this is also it is the this one C is the size of the vertical cover of the reinforcement. Okay, now when we come to the top river, now let me omit this one, and if it is required I will add. later after just checking the reinforcement bar. Now let's come to the dowel here. Now the dowel is it should be now let me use it is 60 millimeter diameter rebar, and the hook it is 90 degree, and the hook bottom it is also 90 degree. So I can use 3 by 3, this side 3, and this side 3, and this side 3, and this side 3 reinforcement anchorage lengths. So the distance from this up to this, that is LC, it should be 0. So to make it 0, it has to be 0. Okay, here. So now the stirrup, when we come to the stirrup, it should be greater than or equal to 6 millimeter, but that is better if we make it 8 millimeter. So this is the grade. Now this is the angle, and S is the spacing between the data bar, which is, let me use it, T1. Okay, this is the cover. So now click OK. Now robots will show the 3D configuration of the reinforcement bar later. Here, safety factor of top reinforcement in the direction of x-axis 0 less than 1, so we need to provide top reinforcement. Okay, so delete this one, and now click this one. So the previously provided reinforcement bars are not changed here. Well, I can use that provided rebar at the bottom and at the dowels, as well as at the stirrup locations of the footing. So let me just provide the top reinforcement here. It is 40, then it is 90 degree. Here the spacing is 40 centimeter. This is the cover. It is it is 40 centimeter spacing. Here the hook is 90 degree, and the diameter is 40. Okay, and the top reinforcement of the footing is provided. Now click OK, just after providing all the values. So good, no problem is found. That means the design of the footing is okay. So click OK. So here just we need to see the 3D arrangements of the reinforcement bar of the footing and the foundation column. So click this one. Okay, here this is the configuration, and here this is the plan view. Now let me see it as plan zone. This is the plan view, and this is the 3D view. So now let us see the foundation node, or the design reports based on the provided footing size and reinforcement in both x and y direction. This is the foundation node. So in the foundation nodes we can see the amount of movement in x and in y directions, and also the settlement of the foundation code. Here this is the spirit footing, and the basic data, the assumption, the geotechnical calculation according to the Eurocode, because I have already set and selected the Eurocode, the concrete calculation according to this code, Eurocode, the shape selection, that is the square footing. So the size of the footing is here, the geometry and the material and the loads. Many combinations are taken because many columns or many supporters were selected. That is why every footing will take a combinations. Okay, here this is the stress calculation, the limit states, So the foundation weight is taken by default by robots, and the soil weight even. And here the design combination is, the ultimate limit is the design combinations. This is, the cover the critical load combinations that robots uses for the design of the footing. This is the axial load 167. This doesn't include the soil weights and the self weight of the foundation. Okay, here this is the axial load, the total axial load, including the foundation weights and the self weight of the soil. So this is the uplift, this is sliding, this is the tabulate settlement. The safety factor, it is greater than 1, so our settlement is okay. And the stability, our stability ratio is 2.5, which is greater than 1. This is okay. So rotation, the rotation, stability ratio is 30. It is greater than 1. It is okay. Here when we come to the RC design, this is the main objective of this calculation is to show or to fix the side of the footing and the reinforcement. So punching here, punching is okay because the safety factor or the ratio is 5.6, which is greater than okay. Punching is okay. The required reinforcement here is at the bottom. Here my is 87.66 kilonewton meter. This is the moment. So the reinforcement along in the directions of x, along x direction, that is to raise it, the moment about y direction is 5.59 centimeters square per meter. So here we can see this is the minimum reinforcement that the footing needs. So this reinforcement must be greater than the minimum reinforcement proposed by robots. So this is in the bottom reinforcement, and when we come to the top reinforcement also, here this is the movement in y direction, as we have already stated before, as top as bottom zone. Here it is also just it is a similar consideration like bottom zone, and here in x direction. So here there is a column and pier here. The pier reinforcement is provided. So finally, the provided reinforcement must be greater than the calculated reinforcement. So here the moment along x direction, we can use 14 diameter reinforcement bar in along x-axis, and the number of reinforcement is 70 based on the spacing provided during the foundation design. So here if we calculate the rebar area here, just it should not be that much greater than the minimum rebar provided by robots. Okay, here I choose where is the calculator. So calculator. Okay, now let me calculate this 17 times 49 times 3.14. Okay, here it is divided by 2.5, the width. So the amount of reinforcement per meter width is 1046, but here it is 500, 559 millimeters square per meter width. So we need to reduce, we need to increase the spacing of the reinforcement. So just to go to here, because will not be economic. So just to go to here. So here the the spacing has to be revised. So Okay, so we just come to here, the foundation reinforcement. Here, now delete this one. Let's come to here. So the only thing that we are going to change it is the spacing. Here, spacing, it is around. Make it, 20. Make it 20. And the top reinforcement also, it is make 20. Because the number of reinforcements should be decreased from 70. It is 20. Okay. Okay, it is okay. So go to the foundation node. Now the number of reinforcement will be decreased from 17 to maybe 12 or 30. So robots takes more time because my PC is busy. Just go down, go down, go down, go down to the reinforcement. Okay, here this one. Reinforcement, RC. Just come to here, the minimum reinforcement is unchanged because, the thickness and the size of the tank is not changed. Here, the provided reinforcement, it is 12 now, it's decreased. Okay, now let's calculate it. So, 12 multiplied by 3.14 multiplied by this 49 equals to divided by 2.5 meters. Perfect. 738. That means 7.38. Here the minimum reinforcement. Here it is 5.59. Now we will also increase the spacing of the reinforcement, just to be more economical. Just now delete this one. Delete this one. So go to here. So we can make the spacing, which is 20, 25. Here we can make it is 25. So this is for bottom also 25. So we need to make it 25 also. So now run the calculation. So here, okay. Now let's run the calculation. I mean now check the foundation node. Here, just observe the spacings of the reinforcement. Previously it is congested, now it is far apart to each other. Okay, now go down. Go down, go down, go down, go down. Okay, RC design. Required reinforcement. Required reinforcement is the minimum reinforcement, and the provided reinforcement is here. It is 10. Now let's calculate it once again. So it is 10 multiplied by 3.14 multiplied by 49. Okay, divided by 2.5. Very good result. 6.15 centimeters square per meter width. This one is, the required or the minimum reinforcement is 5.6, more or less. It is closer to each other. So our provision of reinforcement is economical. So let me show you the ultimate bearing capacity of the soil that robot calculated. Here it is the set element. The limit state, the soil here. Okay. Now the limit state here, left here. Okay, this is the Q ultimate, the ultimate bearing capacity of the soil here, 0.3, or it is 300 kilopascal. This is the ultimate bearing capacity of the soil, and in order to calculate the the allowable, Q allowable, which is equal to Q ultimate Q ultimate divided by factor of safety. Factor of safety for medium soil, it is it is 2.5. So the Q ultimate is this, the this Q allowable, which is equal to Q ultimate, that is sorry, it is multiplied by, so this equals to which is around so Q ultimate, which is equal to 40 times Q allowable times factor of safety. So from this equation, Q allowable equals to Q ultimate divided by the factor of safety and multiplied by this 40. So this equal to 300 divided by 2.5 multiplied by 40. So this can be cancelled by this one. It is 100. So sorry, we just give ultimate. Okay. Okay. Just make it. This is in megapascal, 300. Kilopascal. It is 0.3 megapascal. It is 0.3 megapascal. So megapascal means 10 to the power of 6 multiplied by Newton per meter square. So here it is 100. This indicator that it is 300 kilo Newton per meter square over so now the Q allowable, which is equal to Q ultimate divided by factor of safety. This factor of safety will be provided by the geotechnical engineer from the laboratory. So Q ultimate is 300 megapascal. That means kilonewton per meter square divided by factor of safety. It may be 2.5 or It may be 2.5 or just now for this tutorial I can use 2.5. So the result will be 120. So the allowable bearing capacity or the allowable bearing capacity of the soil will be 120 kilonewton per meter square. So if I use the allowable bearing capacity of the soil, so the robot will automatically take the service load. If I use the ultimate bearing capacity of the soil, robots will use the factor the load. Okay, so this is the design of the footing on the the if side in this side. So now let me design also in this side. Okay, so select the support here. So just click this one. So go through this one. Okay, select this one. Okay, okay, here delete this one. Okay, now let me calculate the previous. Here there is the okay, now the bridge reinforcement. This error is coming. Just to freeze on the reinforcement, go to the reinforcement option here. I think where is it? This one. Foundation reinforcement here. Okay. Calculate this. Okay. Okay, here. Now let me design. Now let me calculate here. Okay, there is a question mark here. No, the reason is I received element update here. Okay, result for the structure made are out of date. Updates impossible. So we need to recalculate the still structure here. It is result is finite element method out of date. So now let me run the calculation once again. Here to do this, go to analysis, run the calculation. Now robot will update the results. Here now the analysis is completed without any error. So let us go to the foundation. So here now updates the foundation here. Foundation 6 up to 341 is updated based on the updated analysis result here. So now it is now close this one. So now calculate. Now robot calculates the size of the footing and the size of the reinforcements that has to be used in the footing part. Perfect. Is the right sign is coming here. This shows that our design is perfect. Okay, now update this one also. Here this side, this footing is this side, and the previous one is this side. Okay, it's updated. Now close this one. So here let's check once again the reinforcement bar, whether it is designed or not. The foundation view. Okay, it is 2 meter by 2 meter, the size is, it is 2 meter by 2 meter. Now it is not optimized. Now let me optimize the 2 meter, 2 meter, it is 0.5. The depth of the footing. And here it is 1 meter height of footing. So fix the H1 and H2, that means the thickness of the footing and the height of the foundation column. So the length and the width of the footing will be iterated by robot. So when we come to the column, it is 0.6, width by 0.6. So eccentricity, 0 eccentricity, that means the I section will be located at the center of the footing. So when we come to also the pier, here this is the plates. So the size of the plate is it is 0.5 by 0.5. Okay, here now apply. Here now the plate is applied to the foundation here, the foundation column, the plate here. So let us calculate. So before that we have to set the ultimate bearing capacity of the soil here. This is the ultimate bearing capacity of the soil, which is 0.3. Robot provides the ultimate bearing capacity of the soil. So we can convert this into the allowable bearing capacity of the soils if we can have the factor of safety just by dividing this value with the factor of safety gives the allowable bearing capacity of the soil. And in that case, if we use the allowable bearing capacity of the soils, robot will use the service load. But if we use the ultimate bearing capacity of the soil, so robot will use the factor load to determine the size of the footing and the associated parameters. So now this is okay. So now here run the calculations. Now here after the calculation, the size of the footing will be automatically optimized here. It is it is 1.7 by it is 2.2. Oh, here it is rectangular footing, but during optimization we need to select the square footing. So now recalculate again recalculate again. So the footing under the internal indie columns will be automatically calculated here. T is 2.1. So 2.1, 2.1. So here we can calculate by this actual size. So now 2.1 square footing will be used at the gable sides of the warehouse. Okay, here we can see the foundation result here. All those parameters are greater than the limiting value, and in the case of also the ultimate limit states, all those values are greater than this limiting value. So this indicated that the size of the footing is okay. And when we come to also the design combination, all those are the design combinations that robot uses during the design of the reinforcements and during the design of the footing. Okay. Okay, when we come to also the foundation reinforcement here, this is the arrangement of the reinforcement. Here there is a top reinforcement here, and there is a bottom reinforcement in both x and y direction, and here there is also the foundation column. Here there is also a pillet. So there is also type R at the foundation column. So now as I'm going to design a new reinforcement, so we need to delete the existing reinforcement. So here click the typical reinforcement here. So we need to provide both the bottom and the top reinforcement. So here the diameter is 40. So we need to use 90-degree anchorage at the top and at the bottom. Here we can easily notice 22. We can easily 25 centimeter spacing here, both x and y direction. This is a cover as it is, and the top reinforcement also. Okay, now let me check first with the bottom reinforcement. So the dowels are the 60 millimeter in diameter and 90-degree anchorage at the top and at the bottom. Here the number of reinforcement is 3 by 3. That means 3 in this direction, 3 in this direction, 3 in this direction, and 3 in this direction. So here this length is 0, so we need to make it 0. To make it 0 this one, I have to put 0 here, so this will be automatically 0. And now the other is the stirrups for the foundation column. Here can use this one, and here this is the anchorage. So now here so now here the spacing is 20 centimeter. So now click OK. This way here the foundation reinforcement is applied here. You can see clearly here the foundation. Here there is no any error, so the bottom reinforcements are sufficient just to resist the moment. No need of providing the top reinforcement here. Okay, so here this the foundation design is the green lights can see here, and we can observe and we can see the foundation mode, whether the reinforcement bar is economical or not. Okay, just to go down here, the reinforcement bar. Oh, record reinforcement. Safety factor of top reinforcement directly exceeds this one. So we need to provide top reinforcement. So here, just to go to here, delete this one, and you come to here, just provide top reinforcement. So top reinforcement with the diameter of it is 40 and anchorage it is 90 degree. So the spacing is it is 20. I mean it is 20, 25 centimeter spacing for both x and y directions must be provided at the top zone of the footing. So now just here it is 40. Now click OK and observe whether there is an error or not. Here just go to the foundation node. The foundation node will provide all the detailed calculations and remarks, and if there are errors, even errors can be clearly seen in the foundation node, so that an action will be taken just to avoid those errors. Okay, come to here. Just the reinforcement here, the minimum reinforcement is provided here. So diameter 14 by 8 reinforcement. So just to go to tools, calculate the reinforcements area per meter width. Okay, here now the robots exports or the loaded to the foundation here, the foundation one. So to view the loads, just click this load definition. Sorry. Okay, so view first the structure, whether the footings are assigned to the support or not. Let's click this one. Okay, perfect. So the columns are assigned. So just come to the foundation view. Yeah. So here this is fixed, and the pier is also it is bolted and fixed. The plate here optimization is it is a square. So apply the calculations. So robot will provide an automatic sizes of the footing here 2.3 by 2.3. Perfect. Now let's check the foundation result here. Oh, there is a problem here. There is some problem here because the loads are not exported. Loads are not exported here. So just let's come to so select the support here. Just let me see the note. It is 394. video here while selecting the node here. Okay, so just exporting the lot. Okay, lots are coming here. Now click OK. And just come to the foundation. But this is okay now. Like to just come to here, the foundation. We can now click apply. So just go to here. Cancel. Okay, just here. This is the load exported to the foundation. Okay, it's good. Just come to here tools and the template, and then here I have already provided this one. Now let me check the foundation results. Okay, because I didn't run the calculation. Okay, run the calculation here, then the results will be displayed here. Perfect. Here this is the values are greater than the limiting values. Okay, here there's a load combination, and you just come to the foundation reinforcement here. So here just let me delete this one because I don't need. Also here just go to the typical reinforcement. So the bottom reinforcement here, it is 14, but it is 14, and here it is 90, it is 90. So this here, this is 25, and this is it is 25. So when I come to the top reinforcement, it is 40 because top reinforcement is necessary, as I have seen in the previous footing. Here it is 25, and here it is 25. So now anchorage is provided, and the dowels it is 16, anchorage is 90. So when I come to here, the number of vertical reinforcement that the column is provided, and the start the anchoring length is 0. So when I come to the stirrup, it is 8, and the spacing is 20. So just click OK. So now robots will put the 3D arrangements of the reinforcement bar here. Okay. Now let me see the economic uh, uh, perspective of the amount of reinforcement here. Just come to the reinforcement which is provided here. Come to the RC design. Okay, before that, now let me see the foundation view first. That is 2.3. Okay, 2.3. 2.3. Okay, come to this. It is the reinforcement is 9 diameter, 40 millimeter reinforcement bar at the top and at the bottom is provided. Here the same minimum reinforcement is required. So tools calculator, 9 times, it is 49 times 3.14 equals divided by 2.3. I think 2.3 is that 2.3 meter. Okay. No, foundation view 2.3. Okay, 2.3. So need to calculate once again. Okay, 9 times, it is 49 times 3.14 equals divided by 2.3 equals, that is 6.02 centimeters square per meter width of reinforcement is required. Oh, it's good. It's good. So our reinforcement bars are economical. So this make it safe. Oh, let's come to the structures back. So very good. So here, this is, this is the footing design. So, this is, the so now here this is, I think, all about the detailed design of footing, as well as detailed design of the structural member of a steel warehouse. So I think this is all about this tutorial. Next time I will show you the detailed design of connections, that is steel connections, the base plates, and the eave connection, as well as the apex connections of this warehouse. So bye bye.